All right, last time we started this section, just briefly, section 2.4, we were talking about the chain rule. Chain rule helps us to find derivatives of composite functions. So composite functions are functions where one function is embedded inside of another one. And this was the derivative rule that we had. Let me delete those pieces off of there. And so when we take the derivative of a composite function, we take the derivative of the outside function and rewrite the inside the way it was. And then we multiply that by the derivative of the inside function. We had done a couple of examples, and we got to this one where we talked about the fact that there's two very different ways of looking at this. And when you take the derivative, they look different initially. If you clean them up with algebra, of course, they simplify down to the same thing. But I wanted to show you how to do the problem in two different ways, and then you can decide which one you like better and kind of go with that one from here on is fine. So one option that we noticed that we had is we had a quotient, right, a division piece that is raised to the power 1/2. So this is the first way that I'm going to do the problem that we identified. So if I think about the problem in that fashion, I have a 1/2 on the outside, and I would bring this is h prime of t, I would bring the 1/2 down, and I would rewrite what is inside of it as is, so I'll do that in a minute, and I would decrease the power by 1. So 1/2 minus 1 is negative 1/2. Now the part that's inside stays the same. So right now the inside part is a quotient. It's 3t squared minus 2 over 2t plus 3. Okay, is that okay? All right, then we have to take the derivative of the inside. Well, the inside, as we mentioned, is a quotient, so we need the quotient rule. So the quotient rule says that I do the denominator, so that's 2t plus 3. Actually, I don't know that I need the outside parenthesis quite so much. I'll just leave it off. 2t plus 3. And I need the derivative of the numerator. So what's the derivative of 3t squared minus 2? 6t. And then the quotient rule says I'm going to subtract. And then I'm going to do the opposite. Okay? So I'm going to do the numerator, as is, 3t squared minus 2. Times the derivative of the denominator. And what's the derivative of 2t plus 3? Just 2. And all of this is written over the denominator squared. So 2t plus 3 squared. And for the gateway, we would stop right there. I want to show you the other option in terms of gateway, and then we'll simplify one of them or the other. And it doesn't really matter to me which one we simplify, but I'm not going to simplify both of them with algebra. That's not really what I want to focus our attention on time-wise. But I want to show you that you can do it in another way. So this is option 1, and then we'll look at option 2. So option 2 treats this as though I have a chain rule on top and a chain rule on bottom, and overall I have a quotient rule going on. Okay? So if I treat it in that fashion, I will do the quotient rule, because that's my outside function. And in the middle of doing the quotient rule, I will apply the chain rule. So the quotient rule says I do the denominator. Well, the denominator is 2t plus 3 to the power 1/2. That's the denominator, right? Where I applied, it's the second, I didn't write it up there, but it's this one right here that I'm looking at right now. So my denominator, and then I will have, I think I need a little bit more space. We're going to just shift this over a bit. And then I'll increase the size here. All right, and then we need the derivative of the numerator. Well, the derivative of the numerator, a chain rule, says I bring the 1/2 down, and then I rewrite the inside. So the inside was 3t squared minus 2 to the new power, which is negative 1/2. Okay, so that's the chain rule part of the outside of the numerator. And then I multiply it by the derivative of the inside of the numerator. So the derivative of the inside of the numerator, that's the 6t we saw a moment ago. Still going to end up with not enough space. We're just going to move it down here for now. I'll shift it later. Okay. Then I need to do subtraction, and I need to do the opposite. Now I need to simply rewrite the numerator. Well, the numerator is 3t squared minus 2 to the power 1/2, and I do the derivative of the denominator. All the chain rule, derivative of the denominator says I bring my 1/2 down, I rewrite the inside, 2t plus 3. And I decrease the exponent by 1. What's my new exponent? Negative 1/2. And I multiply by the derivative of the inside. What's the derivative of the inside of the denominator? 2. And this is all written over the denominator squared, which is probably the nicest part of this particular problem. What happens when we square something that's square rooted? Yeah, the square and the square root eliminate one another because they're inverse operations. So the denominator is actually just 2t plus 3. Square root squared, 2t plus 3. So that's a distinctly different way of doing the same thing, correct? All right, I will simplify the algebra on one of them, and it doesn't matter to me which one. Which one do you want to see the algebra simplified on? The first way I did it or the second? First? Okay, I'm hearing first. I saw a couple of people say second. We'll do first. I'm just going to move this one out of the way since we're not using it right now. Whoa, whoa, whoa. I still got that. Let's try it one more time. Okay. All right, so I'm going to just shift this up here over to the side, and we're going to work with the original one that we had done before. All right, so on this one, it's kind of messy that we have a negative 1/2 power, right? So one of the things that we will do with that negative 1/2 power is we're going to make it positive. How do we make an exponent positive? You turn it into a fraction. So if it's a negative exponent, often we drop it into the denominator. This time, though, it's a whole fraction, right? It's got a numerator and denominator. So how will that look a little different than that? We do the reciprocal. We're going to flip the fraction upside down, and that will make it a positive 1/2. Does that make sense to everyone? Okay. So we're going to have h prime of t. I still have the 1/2. We'll deal with that in a little bit. And I'm going to flip this upside down. This is 2t plus 3 over 3t squared minus 2. And it will be a power that's now a 1/2. We're going to apply the 1/2 and put it back in radical form and all that later. But let's clean up this second parentheses set, or the quotient rule part of it anyway. So we'll distribute our 6t through. So if I distribute, whoops, there we go. If I distribute our 6t through, so 2t times 6t would be 12t squared. And then 3 times 6t would be 18t. Then we're going to distribute both the 2 here and the negative. So negative 2 times 3t squared would be negative 6t squared. And then negative 2 times negative 2 would be positive 4. Okay, is that all right with everyone? Okay, the algebra simplification for this one's just ugly. It just is. One of the things that we're hoping to do, of course, was to multiply everything out in the numerator, which we did. We'll combine the pieces that we can in this numerator. But the other thing that you should notice in terms of like when do I know I'm done with simplifying is that right now I've got 2t plus 3 to the power 2, and over here there's also a 2t plus 3, and it's got a power 1/2. Somehow those have to be combined together because they're the same piece, 2t plus 3, the same factored piece, right? But with different exponents. But I should be able to combine them in some way. So that's going to be one of our goals as we're cleaning this up. So let's take a look at combining the numerator on the second set first. 12t squared plus 18t minus 6t squared plus 4. What will that become?
6t squared plus 18t.
Yeah, these two pieces combine, so I have 6t squared. The other two pieces do not, so we'll simply rewrite them. While I do that, I'm going to go ahead and distribute that power 1/2 to the numerator and denominator respectively. So this is 2t plus 3 to the 1/2. And then we have t squared, 3t squared, good grief, 3t squared minus 2 to the 1/2. It's probably also worth noting that that 1/2 that's being multiplied does have the ability to simplify. Can you see how? Yeah, this 1/2 applies to everything, right? But because it's all multiplication, right, like this is being multiplied by this is being multiplied by this, we can change the order. And so I can actually multiply it by this numerator here. And so that 1/2, that 2 in the 1/2 will cancel with each of these because they're even. So that's actually a very nice cancellation step. So we'll do that here in just a second. But I also want to deal with the fact that this is a 1/2 and this is a 2. So I've got 1/2 on top. I've got 2 on bottom. What can I do? Okay, so we could, let me go with the way you said it. Actually, I like that. So this 2 right here is the same as like 4 halves, right? Yeah? So I could write it like as 1 and 2 halves, or, oh, that blue's not a very good color. How about we use a darker one? So, hang on, I'll do it that way. 1/2, a 1/2, plus 1/2, and 1. I'll write it like that. Or you could do it as 1 and 3 halves. Maybe that's better. We'll do it that way. Okay, 1/2 and a 3 halves. So I can actually rewrite this denominator. One of the ways, anyway, is 2t plus 3 to the 1/2. And 2t plus 3 to the 3 halves. Is that okay? I'll describe it in another way, too, if you're not liking that particular option. But it is very nice to think about it that way. And then what happens is, I've got so much going on. Let's see. Let's reduce each of these. So that numerator will actually now be 3t squared minus or plus 9t and plus 2. This numerator over here, they all stay the same. 2t plus 3 to the 1/2 and 3t squared minus 2 to the 1/2. So I end up being able to cancel these 2 out. The other pieces don't have a good way to combine. I've got this piece still in the denominator, the 3t squared minus 2 to the 1/2. I've still got a 2t plus 3 to the 3 halves. The numerator will not factor in a way that's going to combine with any of these. You're welcome to try and factor them if you wish. Sometimes they will, but it's kind of uncommon when they do. So I have as my numerator now 3t squared plus 9t plus 2 over 3t squared minus 2 to the 1/2 times 2t plus 3 to the 3 halves. So this is going to be one of the most simplified versions that you could use. You could also deal with the fact that these 1/2s are in square root form. So another option for writing this in a way that would be as simplified as possible, or an equal simplification version, just in case you were to see it written somewhere else, or if you were checking or something online or something like that, like a calc site, they might actually write this as the square root of 3t squared plus minus 2. And they might write this as, did I mess something up? Okay. 2t plus 3, either like this, or they might combine these two. So 3 halves is 1/2. This is one of them. This is the other half. So you might see it written that way. It's not any better. I'm not telling you that it's any better. I just want you to know that if you saw something spit that out to you as you were trying to like confirm a solution online or something as you're practicing, you're not wrong if you had it written the first way. It's just an alternate version. Okay? Another way that you can think about it, if you don't want to do this idea where we changed it into the 1/2 and the 3 halves, is you could actually subtract. If you have the numerator as a 1/2 power, right? Like think about properties of exponents. If you have a to the 1/2 over a to the 2, you can actually subtract 1/2 minus 2. And 1/2 minus 2 is negative 3 halves. And negative 3 halves dropped back down to the denominator would be the positive 3 halves we had before. It's a property of exponents that's happening there. So if that's more appealing to you, that is another way to think about simplifying those radicals. Okay. On the gateway, however, on Wednesday, that very first step, either version 1 or version 2, would be what we were looking for. Okay, any questions on that? Should I do some easier ones? That's the ugliest one we're going to do. And we're going to get it, we got it done first thing. It's good news, right? Good news. All right, let's take a look at ones that are a little bit easier. So again, no trig may not be your thing, but in terms of derivatives, trig's really nice because the derivatives for trig functions are very clean. It's the derivatives for quotients and chain rules that end up being kind of messy sometimes. So this one's actually not too bad. I know you don't see a set of parentheses here, but do you know where the set of parentheses are understood to be? Where is there some understood parentheses here? Yeah, around the pi x. So anytime that you have a trig function of something, like if you try to put it in your calculator, it will force the inside to be sort of an inside of a parentheses. Depending on the operating system, it might even put the parentheses on for you. Mine does. And so understanding where those parentheses are is helpful in determining what the inside versus the outside function is. The part that's in parentheses is inside function, which means the outside function is the sine. Okay? So what is the derivative of sine? Cosine. And anytime we're doing chain rule, we simply rewrite the inside piece. That's the pi x. And then we take the derivative of pi x. Now, I know pi x feels kind of funny because pi is a letter. It's a Greek letter. But it feels kind of funny. But it's just like having 3x. The derivative of 3x would be 3. So Daniel's right. The derivative of pi x is just pi. Okay? And the only thing you can do to simplify or to clean this up is to simply move the pi to the beginning, which you might have wanted to do if you were doing it on your first step through anyway, if you wish. There's no other simplification that can happen. That's it. We all breathed a sigh of relief, right? So much better than the last one for simplification. Any questions on that one? Okay, let's try another one. What do you notice about this one? First, let's talk about where you see some parentheses. Do you see some parentheses here? Yeah, around the 3t, much like the pi x in the last problem, right? What else is different about this problem than the last one, though? Cosine is squared. And the way it's currently written, while it's nice and compact, we've talked about that, it's not very friendly for thinking about it in terms of the composite functions that are present. So I'm going to rewrite this in a different way to sort of identify what's really going on. There's a 5. It's not squared, right? What's squared is cosine. The 5 is not squared. So I'm going to rewrite then the cosine and the 3t, and all of that is squared. Okay, is the rewriting step okay? So this is the first one we've encountered like this. There are 2 inside functions. 3t is inside, but the cosine part is inside as well. So what do? Well, we apply the chain rule twice. And here's what it looks like. The outside function is the power of 2. So what do we do when we have, so it's almost like you're going to ignore everything right here for a moment. Power of 2, what do? Multiply down, bring the 2 down, so 2 times 5 would be 10. And everything that I just covered up in red gets rewritten. So cosine 3t. And I decrease my power by 1. 2 minus 1 is 1, so you can choose to write it or choose not to write it. It doesn't matter. A little bit small. So the first inside function piece is the cosine part. What's the derivative of cosine? Okay, so now we've got, this is my inside I'm going to ignore for the moment. It's what?
Negative sine.
It is negative sine. And it's negative sine of the same thing that's already inside of it, which is a 3t. Okay? Please make sure that if you open parentheses, you close them in appropriate places. We want to make sure that we're getting the multiplication factors the way we intend for them to be, and parentheses indicate that. So do be careful on that. I'll be looking for that when I grade things too. Now, the part that's in red that I sort of covered up here, we need the derivative of that piece. So it's the derivative of 3t. It's just 3. Let me see if I can take off the red. Yep. So gateway purposes, you're done. You've done the inside part twice. You did the inside that dealt with the cosine, and then you did the inside that dealt with 3t. For the purposes of what we're doing right now, we're going to clean it up a little bit. We can clean it up a little bit. It's not too bad. I can take the 10 at the end and the 3 at the, 10 at the beginning, 3 at the end. I can multiply them. And I can also take this negative right here that's on the sign, and I can use that. So I can bring that out and make it a negative 30. Because cosine 3t is raised to the 1 power, I don't really need the 1 power. It's really just cosine 3t. And I already dealt with the negative with the sine 3t, so now I just have sine 3t. Hang on. If you did parentheses around the cosine or around the sine, that would be fine. They aren't really necessary because we put the 3t in the parentheses. So this would be a perfectly acceptable way to write it. Good? Okay. One more with these directions where we're just simply finding derivatives. We have this function. I specifically do this example because I want you to pay attention to where the squared is. What's squared? Pi x. Over here, what was squared? Cosine. You need to be very careful, right? The location of the square matters. It changes things quite a bit. And in fact, it's easier with the one we're about to do for it to be on the pi and the x. Now, if you wish, you don't have to, but if you wish, you can actually distribute that pi x to the squared part through first. So you could write this as the cosine of pi squared x squared, and then you have only one inside function. That's kind of friendly. Okay, if you leave it as the squared, you kind of have two inside functions like the last problem, which means we have to apply the chain rule twice. Okay, so let's get started. So this one's y prime. Derivative of 3x is 3. And then we have the negative 5. So the negative 5 will stay. My outside function right now is cosine. So what's the derivative of cosine? Negative sine. So if you wish, you can actually change this to be a positive 5 sine at the moment. Just use the negative that's coming out of that all at the same time. And the inside gets rewritten. It's pi squared x squared. Okay, so this is the derivative of the outside piece that we just did. Now I need the derivative of pi squared x squared. Okay, please do not let yourself be confused. Pi squared is just a number. It's a constant. So the pi squared just comes along for the ride, and you can flat out rewrite it like that. If it had been the number, say, 4, we'd just write 4. We wouldn't really write 4 squared. You probably would write 16, right? You probably would. But there's nothing wrong with it just being written as pi squared, okay? But we do need the derivative of the x squared. And so what's the derivative of the x squared? Yeah, that's 2x. So either you can write it like here as 2x. That's fine. Or if you wanted, you could write the 2 in front of the pi squared and write the x at the end. Doesn't matter. And there's not a lot of simplification on this either. Are you starting to like trig functions just a little bit better? Simplification on them doesn't occur quite as frequently. This piece here and the 5 at the beginning can combine, and that's about it. So my y prime will be 3 at the beginning. And then I have the 5 and the 2 pi squared x, making it 10 pi squared x, and then sine of pi squared x squared. Any questions? Okay, we have just a couple of more. Number 7. Number 7 is actually a far nicer function than most of them that we've been working with, so that's good news. But there's a bit more in terms of the directions. They want us to evaluate the derivative at the given point. So this is not something that'll show up on your gateway. All the gateway questions will look like these. Just find the derivative, find the derivative, find the derivative. On this one, we find the derivative as well, but then we evaluate it at x equal -2. That's the only thing that's different. At the end, we plug in x equal -2. Now, we saw a function like this last time, and I talked about the fact that that denominator, I mean, you can do the chain rule or the quotient rule if you wish, but it feels a little bit funny because the coefficient on top is just a number. It feels a little funny to do the product or the quotient rule. The chain rule is a really nice way to do the problem. If you would like to try it that way, we just write the denominator all inside of a parentheses with a negative 1 exponent. And then we'll take our derivative. Okay, so the chain rule says my outside function is the negative 1 part. So I take the negative 1 down in front. So I've got negative 5. I rewrite the inside. And what is my new exponent? Negative 2. And then I need the derivative of the inside. So what's the derivative of x cubed minus 2? 3x squared. Okay, so for the purposes of the gateway, if we were just finding the derivative, we would be done. That'd be fine. I need to evaluate this. Technically, I don't have to clean it up to evaluate, but it's usually helpful. And this is one where it is helpful to clean it up just a little bit before I evaluate and plug in negative 2. So I'm going to do that. The negative 5 and the 3x squared will be on the numerator. So that's negative 15x squared. And then the piece that's to the negative 2 power will drop back down into the denominator. So x cubed minus 2, and it now will have the power 2. That's the only cleanup that can be done from an algebraic standpoint. And what we would be doing next is we would be evaluating it at x equal to 2. So we come back down here. We're going to find f prime of negative 2. So I have negative 15 times negative 2 squared over negative 2 cubed minus 2 squared. We'll start with the top. Negative 2 squared is 4 times negative 15 would give me negative 60 on top. And you're welcome to use your calculator to simplify these quicker. That's fine too. Here, I've got negative 2 cubed, which is negative 8 minus another 2 gives me negative 10, and negative 10 squared gives me 100. You can simplify negative 60 over 100 either in fraction form or decimal form. In fractions, it's negative 3/5, or if you want to use decimals, it's negative 0.6. Remember, decimals are fine if they're terminating. If they're repeating, we want to leave it in fraction form. Is that all right? Okay. Last one goes one step further, and we saw this happen back in sections 2.2 and 2.3, where we did a bunch of derivatives, and then we plugged in a value, and then we found lines. So that's where we are. We're going to find an equation of a tangent line. And once again, when we actually have to do one step further, the problems are usually easier to do the derivative of. So there's a little bit of give and take with that. Yes, you have to keep going and do some additional step at the end, but there's usually less cleanup and simplification. They're not quite as messy. So on this one, we're going to start by finding a derivative. Okay, so it's a chain rule because I have something to the power 2. If you wanted to, you could square it out and not use chain rule at all, right? You could. It wouldn't hurt anything. There's totally fine if you try to do that way. We're going to do it with chain rule just because that's what we're practicing right now. So we have something to the power 2. The power 2 will come down to the front. We'll rewrite the inside, 4x cubed plus 3. What's my new power? 1. So either write it or don't, your choice. And then I need the derivative of 4x cubed plus 3. 12x squared. This is actually not a bad example of a place where simplifying is sort of optional. If you want to plug in x equals negative 1 at this point, you certainly can. So we're going to do that just because we can. If you need to simplify it for the directions of the problem, just simplify it one step. That's fine. It's not a difficult one to simplify. But we could also just evaluate at this point if that's where we're headed in the particular problem. So this is y prime of negative 1. So I have 2 times 4 times negative 1 cubed plus 3, and then 12 times negative 1 squared. So the 2 will stay at the beginning. Negative 1 cubed is negative 1 times 4, negative 4 plus 3, negative 1. So that entire first piece reduces or simplifies down to -1. -1 squared here is 1 times 12 is 12. So we have 12. And if I multiply 2 times -1 times 12, I get -24. Okay? Okay, you saw us do this before. We found a slope. That's what this is. A derivative is a slope. It's a slope specifically of a tangent line. So we now have a slope. And we have the ordered pair, x, y, it's -1, 1. So if we use y minus y1 equals m times x minus x1, it's not the only way to do it, but it's a pretty nice one. My y1 value was 1, so this is y minus 1. The slope I just found was -24. My x1 value is -1, so I've got minus -1 here, or you can write it as just +1. So we're going to clean this up to solve for y. Y minus 1 equals -24x minus 24. And if I add my 1, my equation becomes y equals -24x minus 23. That's what I'm asked to find, the tangent line at the point -1, 1. I'm going to shortcut the graph step. I'll just sketch it for you. But what it's asking you to do is to graph the original equation and graph the line that you just found and verify visually that it makes sense, that it really looks like a tangent line. So if you were to graph the first one and then the second one, they'll look something like this. Hang on, let me get a little bit more space here. All right, so the graph looks like this. Excuse the scale. And it has one that looks like that. So this is not drawn to any kind of scale, but you do get a tangent line. That tangent line, although the scale looks terrible because of what I've drawn it, is actually at -1, 1. I know my scale looks terrible. I've said it 3 times, but we're okay. All right, so if you graph it on your calculator, it will look something like that, depending on your window.